Hello everyone, my name is Bore Yang, and I'm very glad to present our work, SrcMarker Dual-Channel Source Code Watermarking via Scalable Code Transformations. So recent years have witnessed a rapid expansion of our developer community. In 2023, GitHub reported over 100 million developers. And with this rapid growth, also comes concerns that open source code might be used maliciously or against their license, which calls for a way to protect the copyright of developers. Additionally, the rise of large language models has further complicated this situation. In 2022, shortly after the release of ChatGPT, Stack Overflow issued a policy that banned AI-generated contents on its platforms. This is because large language models have been found to sometimes generate plausible code or responses, which could be potentially harmful to the community. Therefore, we also need a way to distinguish machine-generated code from human-written ones. To deal with these problems, we propose SrcMarker, a watermarking system for program source code. SrcMarker is capable of embedding bit strings into code snippets as an indicator of ownership. It contains an embedding module to encode watermark into functions by performing semantic preserving code transformations, and an extraction module to later extract this watermark. SrcMarker provides a way to proactively protect code ownership. Consider the case where a developer wants to protect its code from unauthorized uses. It could first embed a watermark into its code before making the code public. And now if we assume an adversary who downloads the code, makes slight modifications, and claims a false ownership, the developer could then prove its ownership over this piece of stolen code by extracting and verifying the watermark. Actually, digital watermarking is a long-established field. Unfortunately, few works exist on watermarking source code, and existing methods from other related fields could not be directly applied as they work under other different assumptions or constraints. One related field of work is software watermarking, which embeds watermarks into software executables by injecting hidden control flows or secret runtime behaviors. However, such methods typically target compiled binaries and have no readability constraints. Another line of related work is text watermarking, which embeds watermarks into natural languages by performing word substitutions or sentence structure modifications. However, these methods tend to ignore the syntax constraints of programming languages, which risk breaking code syntax. Therefore, it is actually non-trivial to design such a watermarking system for source code, as source code has its own nature and constraints. Source code is subject to constraints in both natural and formal channels. The natural channel is typically used by human developers for understanding the code, and the formal channel is usually used by tools such as compilers for automated processing. It is then required that our system must preserve both the natural and formal semantics of the code. Additionally, the system must balance multiple requirements for the watermark, including accuracy, efficiency, transparency, robustness, and capacity. And finally, unlike images, which lie in a continuous space, source code is essentially a sequence of discrete strings, and such discreteness also brings about additional challenges, as we cannot directly use gradient-based optimization methods to encode the watermark. To deal with these challenges, we incorporate 4 specific designs in SrcMarker. We first propose to use rule-based semantic preserving code transformations for encoding the watermark. Such transformations are guided by the abstract syntax tree, or AST, of the input code. The abstract syntax tree is essentially an equivalent structural representation of the original code, and by operating on this tree structure and leveraging its structural information, we can theoretically ensure the semantic equivalence of the watermarked code. And second, we follow the dual-channel nature of source code and embed watermarks into both channels. We perform variable renaming in the natural channel and code structure transformations, such as converting a for loop into a while loop, in the formal channel. This not only increases watermark capacity, as we now have a larger space to work with, The two channels also serve as mutual backups and improves robustness. And third, we introduce neural networks in the embedding and extraction processes to reduce the manual effort that would otherwise be required for designing a pure rule-based system. And finally, since the code transformation contains discrete operations which are not very compatible with our learning-based backbones, we propose an approximation method for such discrete operations that work entirely in the continuous feature space of neural networks, thus enabling the end-to-end training of this entire system. And with our design clarified, we now illustrate some of our implementation details. This figure illustrates the overview of SrcMarker. It contains three components: the watermark embedding module, the watermark extraction module, and the feature approximation module. We will start from the embedding process. The embedding module uses a set of neural networks to extract feature vectors from the input source code and watermark. The network then selects a set of transformations to be performed. And on top of that, a rule-based transformation pipeline executes the actual transformations to encode the watermark. And specifically, for this rule-based code transformation pipeline, we would like it to be efficient, sound, and work on multiple languages. Unfortunately, existing tools either have some slight implementation issues that harm their efficiency or soundness, or they target specific languages, which limits their usage. Therefore, we implement Mutable AST, which proposes a unified AST representation that hides away language-specific details. This design allows transformations to be performed across languages in a unified manner. Benchmark results also show that Mutable AST achieves better efficiency and correctness compared to other existing code transformation tools. Then the watermark extraction module follows a similar learning-based design and uses neural networks to extract the watermarks. And finally, the feature approximation module bridges the non-differentiable gap between the embedding and the extraction processes. While source code is discrete in its input space, it is internally represented by continuous feature vectors inside a neural network. And any changes made to the code itself will eventually be reflected by some corresponding changes in this feature vector. And based on this idea, the approximation module uses the original code's feature and the selected transformations to produce an approximated version of the transformed code's feature. This approximated feature could then be used as a differentiable substitute for the transformed code's feature. This approximation process happens entirely in a continuous and differentiable feature space of neural networks, and we can thus simulate the effect of the discrete code transformations in a differentiable way. As is shown in this figure, while the original gradient backpropagation from the extraction module is cut off due to the discrete operations in the embedding process, the feature approximation module bridges this gap by introducing new gradient data flows, allowing this entire system to be trained end-to-end. And we then move on to the experimental evaluation of SrcMarker. Our evaluation uses 3 different datasets covering 4 different types of programming languages. And for baselines, since fewer works exist on source code watermarking, we use 2 representative works on text watermarking, namely the AWT from S&P 2021 and CALS from AAAI 2022. We adapt their methods to source code and use them as baselines. Our evaluation mainly focuses on function-level watermarking, where we embed a 4-bit watermark into a function. Here we mainly consider the effectiveness, transparency, robustness, and capacity of our system. Additionally, we also consider a more practical project-level watermarking scheme, where we aim to protect an entire source code repository. And we will start from the function-level watermarking setup. The effectiveness evaluation covers accuracy and efficiency, measured by bitwise accuracy and the encoding and decoding time of the watermark, respectively. Results here show that our method achieves comparable performance with the baselines in these aspects. And for transparency, we mainly consider the preservation of operational and natural semantics. For operational semantics, we perform AST-based syntax checks on the code search net or CSN dataset, and execution-based tests on the MBXP datasets. For natural semantics, we compute the code blue and MRR scores. The code blue measures the distance between code before and after watermarking, and MRR is calculated on a downstream task, a code search, since we expect the watermarked code to remain consistent with its original natural language description. Results show that SrcMarker well preserves both operational and natural semantics, outperforming the baselines. For robustness, we assume the goal of an adversary is to remove or corrupt the watermark without changing the code functionality or impairing its naturalness. We consider two types of attacks. We first consider a random removal attack, where we assume the adversary only has a general knowledge that a watermark is embedded via code transformations, but has no further information. We also consider adaptive attacks, where we assume the adversary has full knowledge over SrcMarker. And for random removal attacks, we mainly consider random perturbations on the two channels. In the formal channel, we randomly perform 1 to 3 code transformations. And in the natural channel, we randomly rename a certain proportion of the variable names in the code. We also consider a moderately strong dual channel attack, where we randomly rename 50% of the variable names and perform 2 random code transformations. Results show that SrcMarker is relatively robust to single-channel attacks. This is because its dual-channel embedding design provides additional robustness. On the other hand, dual-channel attacks are more powerful, but they come at a greater cost with greater losses in natural semantics. And we then consider an adaptive adversary who has full knowledge over SrcMarker and can train its own model SrcMarker adversary. We first consider an adaptive de-watermarking attack, where the adversary trains a sequence-to-sequence de-watermarking model on the paired data of its SrcMarker adversary. It then uses this de-watermarker to remove the watermark of SrcMarker. This adaptive de-watermarking attack indeed lowers bit accuracy. However, the de-watermarked code is barely usable, as this sequence-to-sequence de-watermarking model is unaware of the syntax constraints, and it tends to produce broken code. And we also consider an adaptive re-watermarking scheme, where the adversary directly uses its SrcMarker adversary to inject a new watermark into the code watermarked by SrcMarker. In this case, re-watermarking also lowers the bit accuracy of our original watermark, as some of the transformations used by SrcMarker might be altered. However, SrcMarker will not respond to the adversary's watermark, as the accuracy of this adversary's new watermark is still at chance level. This is because SrcMarker and SrcMarker adversary are two distinct models, and the extraction module of SrcMarker will not respond to those changes made by SrcMarker adversary. This also demonstrates the advantage of end-to-end training. And finally, for capacity, as we increase the number of watermark bits embedded in a function, bit accuracy suffers a drop, as it becomes more demanding to embed more information into the already limited space of source code. Nonetheless, SrcMarker still maintains comparable performance with the baselines. Here we provide an example to illustrate the effect of SrcMarker. The highlighted regions indicate changes made by SrcMarker to encode the watermark information. But despite these changes, the code still remains valid and its functionality remains unchanged. Now we move one step further from our function-level watermarking scheme and consider a more practical project-level watermarking setup, where we aim to verify the ownership of an entire source code repository. We can embed a project-level long watermark into a source code repository by decomposing this long watermark into shorter segments and embed one segment into each of the functions within this repository. This project-level watermark could later be verified by extracting the segments and performing a null hypothesis test. This setup allows a longer watermark to be embedded, which could be more practical, as this watermark is now long enough to serve as a unique identifier. It also enjoys increased robustness, as this watermark is now verified by a statistic test on a long sequence. Given that a sufficient number of watermarked functions exist in this code repository, the long watermark could be successfully verified, even under various attacks. This setting demonstrates a more practical use of SrcMarker for copyright protection. And to sum up, in this work we propose SrcMarker, a dual-channel source code watermarking system combining both rule-based and learning-based designs. We also implement Mutable ASD, a language-agnostic code transformation pipeline which we hope would be beneficial for future works in this related field. This is the end of my presentation today, and thank you very much for listening. If you are interested in our work, please definitely check out our original paper. Thank you.